If you're looking for an open source project that will help you to autoscale your Kubernetes cluster, then this episode is for you. Welcome back to the Is It Observable YouTube channel. Today's episode is going to be part of the Kubernetes series where we covered a couple of episodes. When designing reliable and performance workload, we usually quickly add autoscaling solutions available in Kubernetes, which is HPA or VPA. But as a natural consequence of using those solutions, we end up consuming, or in fact allocating, more resources within our cluster. And we realize quickly that we need more nodes to manage the extra replica that we just added. That is why we usually use Cluster Autoscaler solutions, and there are plenty of them. In today's episode, we will focus on an open source solution that will manage the autoscaling of our cluster and also provide features to consolidate our nodes to be more sustainable and cost effective. And I'm referring to Karpenter. If you enjoyed today's content, don't forget to like and subscribe to the channel. So let's see what we're going to learn out of this episode. We'll start by doing a short introduction on what is the current challenges of using the Cluster Autoscaler solution. We'll present, of course, the Karpenter project, and we will specifically talk about the NodePool CRD. And of course, as usual, we'll cover the observability that we'll get out of Karpenter. A few months ago, I released an episode explaining how we could autoscale our workload in our Kubernetes cluster using horizontal pod autoscaler for HPA or vertical pod autoscaler VPA. Kubernetes gave us the luxury to build smaller instances of our pod and rely on autoscaling to provide more replica based on the actual load on our pod. Just to remind, HPA will adjust the number of replica based on a KPI, and by default, it only utilized the metrics available in the metric server, which is CPU usage and memory usage. And usually, scaling on CPU and memory clearly is not ideal. So that is the reason there are projects that resolve these challenges by connecting to a third-party solution to expose external metrics to the HPA objects. To remind, in this space you have Keda. If you want to learn more about Keda, I've built a dedicated episode about it. Otherwise, there's another CNCF project named Captain that provides a metric server allowing you to connect to several observability backend of your choice and use them for your HPA. Out of HPA that adds extra replica, there's another scaling solution which is, honestly, I'm not a big fan of it. It's called VPA. VPA stands for Vertical Pod Autoscaler, and the objective is to adjust the size of the pod resources based on the load. In fact, prior to Kubernetes 1.27, when scaling was required, VPA had to reschedule a new instance of our pod with the new CPU and memory settings, and that basically was quite painful. But since 1.27, it can now adjust the resource directly on the pod without the need to reschedule or restart our pod. I usually see that lots of users are using VPA more in a recommendation mode, where VPA will suggest the requests and limits of our pod based on the behavior. To remind, VPA does not fit for all of our workload. If you're planning to use it for jobs, well, then no, it doesn't make sense. It is not designed for that. So Keda, in fact, has a specific solution for job that will bring more value for you. So check out Keda for the jobs. Otherwise, there is a basic rule out of just the jobs. So every workload that fits in those conditions will never be compatible with VPA. The first one is if your application uses a significant memory at the startup of your pod, then VPA doesn't make sense because your memory allocation usually will be stabilized and even lower once the app is actually running. The other use case is garbage collector. So if you have any runtime that will using garbage collector like Java or Go, then VPA doesn't make sense. But scaling workload is great, but remember, it often happens that we are using a defined number of nodes, having specific size in terms of CPU and memory. If you're scheduling new pods or changing the resource settings of our pod, it means they are consuming or at least allocating more resources within our nodes. And what happens when we try to schedule a new workload in our cluster where our nodes has limited resources left? Well, it will stay in pending states. And we may have an unscheduled event warning us that we have no resource left for this workload. That is the reason we quickly want to utilize the Cluster Autoscaler, or CAS, to adjust the size of our cluster. CAS is actually looking for unscheduled or pending workload and will take action to spin up new nodes that could host our new workload. For information, Cluster Autoscaler are only available for AWS and Azure. For Google, JKE, it completely managed differently. They have a dedicated offering that will do that called GKA Autopilot. CAS, or Cluster Autoscaler, is great, but it requires a couple of configurations within our cloud provider. So first, we need to create a managed node pool. And this is not allowing us to create various type of sizes or instances type, because it's going to be a fixed machine, a fixed type of machines that will be in that management node. You need to have the exact same type of instance for your cloud provider within this management node pool. And then your node pool needs to have its own autoscaling group, meaning that if you need to have different type of nodes, size, or having nodes with GPU, you will have to define the right management node pool and the right autoscaling group. Otherwise, CIS won't make any magic. The other disadvantage of CIS is the fact that provisioning new nodes to resolve an unscheduled issue can take several minutes. In fact, it's even closer to 10 minutes. And when you need to scale, 10 minutes sounds very, very, very long. And lots of bad things could happen within that time frame. So why is it so long? Well, let's explain what is currently happening behind the scenes. So let's get back to the situation where we need more replica to our workload using HPA. Our new pod is scheduled, and due to limited resources, our pod is stuck in pending state. CIS sees it, and it starts to reaching out to first the autoscaling group API, that will then reach out to the managed node pool API, and then it will finally reach out to the EC2 API to create a new instance. So several bounds of API calls are requested to generate a new node in our cluster. So CIS is great, but it feels very slow. And again, if we manage a cluster having no GPU and suddenly someone deploys a workload that requires GPU, CIS won't spin up the desired node because we have no managed node pool available with GPU. So in general, CIS will require lots of tasks to properly work. So creating all those stuff and detecting every managed node pool or autoscaling group required to make it work. That is the reason the open source project Karpenter has been created to resolve all of those challenges. And even more, it can also consolidate our workload. Karpenter is an open source project that is initially been built by Amazon, resolving our need of autoscaling our cluster based on the resource requested by our workload. Out of just autoscale, Karpenter optimized the workload to scale new nodes. Remember, CIS had to query lots of different APIs, so the autoscaling group, the node pool, and so on, to spin up an instance. In Karpenter, we remove all of those layers, and that at the end resolved this long starting time that was required previously with CIS. Karpenter will directly reach out to EC2 to spin up the right instance. So direct call without going to any other layer. So it will be much faster compared to CIS. And if we only consider this feature, this is already amazing. But Karpenter is not limiting in speeding up the process. It will try to optimize the usage of our nodes. Instead of spinning up the fixed type of instances that we've defined like CIS, Karpenter will be able to spin up different size of nodes respecting the configuration that we have shared with Karpenter. It could decide clearly to spin up one node where all the workload will be hosted to optimize our cloud provider usage. When doing so, it will evict pods and decordon the node from the cluster while the other fresh new node it's been spin up. So Karpenter relies on provider. So of course, AWS is the first provider supporting Karpenter, but it's not the only one. We have Azure and Alibaba Cloud, and last there's a current project called the Cluster API, meaning that everything supporting the Cluster API will be supported. GKE is not part of this initiative because they already have a similar way of handling it. But I'm convinced that it would make sense to have a GKE provider for migration perspective. Let me know what you think by dropping your comment on this video. Anyway, to be able to utilize all the features of Karpenter, there are obviously some requirements. And those requirements will really depend on the cloud provider, meaning the admin or the platform engineer will be in charge of implementing the right requirements depending on the cloud provider. And then we simply need to deploy Karpenter using the Helm charts, and we'll end up with a Kubernetes deployment that will also add a Kubernetes services that will expose metrics. Yes, metrics, which means you will get at least a certain level of visibility out of Karpenter. But we will touch base on this later on the Observability chapter. Karpenter will also deploy several CRDs, so we have the NodeClass, the NodePool, and last, the NodeClaim. NodeClass is the CRD that is specific to each individual cloud provider. So in the case of AWS, we will have the EC2 NodeClass for EC2. For Azure, we'll have the AKS NodeClass, and we'll have the ECS NodeClass for Alibaba Cloud. The NodeClass is designed to map the node instance type that would be available within each provider. The NodePool would have a reference to that NodePool class, allowing Karpenter to interact properly with the right provider. NodePool class has many options when configuring it, allowing us to customize how Kubernetes should behave by defining the max number of pods on our nodes, the resource reserve for the systems, the resource reserve for kubelets, how Kubernetes should proceed, evictions, and way more. But the most interesting CRD is clearly the NodePool that will define the type of nodes that we're looking for to autoscale our cluster or to consolidate our cluster. But we'll touch base on this CRD in details later on this episode. Then we have the NodeClaim. This CRD is 100% managed by Karpenter, meaning that we will never interact with this CRD, at least we will never create it. Karpenter will create, delete the NodeClaim depending on the demands of pods in our cluster. So every time we have a pending pod, it will evaluate the resource requirements with the settings defined in our NodePool and NodeClass, and it will create a NodeClaim. At the end, the NodeClaim is a great source of information to understand what is currently happening within our nodes managed by Karpenter. So the flow is the following one. So it's going to create first a NodeClaim, because it needs to autoscale. It will reach out to the cloud provider to provision the right type of instance that is required at that moment. Then it will update the NodeClaim to notify that the type of instance is started. Once the node is available in the cluster, it will update the NodeClaim to track the progress and then add the right metadata to our new node depending on the settings that we've defined in the NodePool. So NodeClaims share the entire history of actions done by Karpenter. So to keep track on the progress on the node provisioning and consolidation, we can simply describe the NodeClaim using kubectl describe NodeClaim. Otherwise, we can also find lots of details on the Karpenter's tasks in the logs of the Karpenter replica. And the other great thing is that Karpenter is adding Kubernetes events to our pod, so we know exactly what is currently happening to our workload when Karpenter starts to taking actions. When managing your cluster with Karpenter, you will need to define at least one node pool, the default node pool. But you are free to create as many node pools as you want. In the node pool, we will assign to the specific node class that we need. So in the case of AWS, we will need to assign it to an EC2 node class. But what is interesting with node pools is that the ability to assign specific taints or labels to the freshly new node added by Karpenter, meaning that we can create node pools for specific type of workload in our cluster. We can define an expiration time. Past that time, Karpenter will drain this node and replace with a fresh new instance. And the most exciting piece, I think, is the requirement sections. In Karpenter, you don't define the exact instance name or type available in your cloud provider, but you're asking Karpenter to find nodes that respect specific specifications in terms of number of CPU, type of operating systems, the type of architecture, the zone, the type of instance, on-demand or spot, and more. For example, as you can see in this example, each provider will provide its own sets of keys to match to their own specifications. So here is the link to the AWS keys to matching the instance types. Here is the link to the Azure types. And last you have, I didn't find the ones for Alibaba Cloud, but maybe if you find it, you can drop this in your comment. In the requirement rules, there's a notion of mean values. It actually defines the number of minimum instances respecting this requirement. So in our example, there will be 2 instances with CMR, 3 on M5, M5D, C5, and R4, and so on. So the requirements piece is great because it can only focus on the resources that we need instead of limiting to a specific instance name available within our cloud provider. The other smart thing is that you can place temporary taints on the startup of the nodes. This is particularly useful when using, for example, CNI like Cilium. You can make sure that Cilium gets deployed first and then the node before any workload comes in that fresh new node. Karpenter also offers a way to control the size of the node pool by defining limits. You can define limits in terms of CPU, memory, or even GPU. This limits means the total amount of CPU, memory, GPU available within that node pool. But the big relevant configuration in the node pool, as you saw in the example, is disruptions. This part of the node pool settings is, I think, the most interesting one. Basically, it allows us to define the policy that Karpenter will use to optimize the node usage. It has many options to fine-tune how the disruption will take place in our cluster. The basic settings would mean only to define the consolidation policy that could be either equal to when empty or underutilized. Meaning that if the node is empty or underutilized, Karpenter will try to spin up different size of nodes to optimize the actual node allocations of a node. It is very exciting because we won't have cluster with tons of nodes doing nothing at the end. So how does it work in Karpenter? So the first step, Karpenter will list all the nodes that could be disrupted. So to determine if it could be disrupted, it will look at the node if it has parts that could be evicted. Once he has this list, he will check if the nodes selected are respecting the budget defined in the node pool. Don't worry, the budget will be explained in a few seconds. Then it will simulate a rescheduling of the pods on the node to see if there would be a replacement and that will fit to the actual situation. If successful, then it will taint the node with Karpenter disrupt node schedule, then spin up the replacement node if that is required, or if maybe not required, it will wait until the workload has been moved to the available nodes and then delete the node. So this notion of budget is playing a major role in this algorithm. But what does budget means in Karpenter? The budget will let Karpenter know how many nodes it could be disrupted. It will define a budget. We can express it either in a number of nodes or in percentage. Depending on the budget, Karpenter will count the total nodes that could be disrupted. And these follow a specific operations. So the total number of available nodes minus the total node that is eligible for disruptions minus any nodes that could be not ready. So let's say we have 10 nodes and Karpenter detects that there's 3 nodes that could be disrupted. It means that this number of nodes will be 7. So 7 nodes will be left. So if we have a budget of 2, then Karpenter will be able to start disruptions because we're respecting the budget. Under budget, we can also define the reason that could be empty, drifted, or underutilized. So we can fine-tune our budget by applying various conditions. So in this example, we tolerate 5 disruptions without any reasons, 20% if empty or drifted, and 0 by launching a cron job on daily basis to remove underutilized nodes. 0 meaning no disruptions allowed, and we are running this every day at the first 10 minutes of the day. To control the workload, to avoid having any disruptions, we can even define specific annotations within our workload. And the annotation is, here it is, Karpenter do not disrupt equal true. We can also place these annotations within specific nodes as well. Out of the amazing feature of managing on Node in a smart way, Karpenter also provides the right visibility to our cluster. If you remember, I mentioned previously that NodeClaims gets all the tasks triggered by Karpenter in a given node pool. But we will need to do a kubectl describes to get everything. Otherwise, Karpenter is keeping track on all the tasks in the logs produced by the various replica of Karpenter. And the great thing is that the logs is in JSON format, so it's very, very easy to parse. It also adds Kubernetes events in the details of the pod where Karpenter has done some actions. So only with this, we can keep track on what is actually going on in the autoscaling and consolidation tasks that Karpenter has achieved. Out of this, Karpenter is having a service exposing Prometheus metrics. With the help of this exporter, we can have details on the node claims. Then we have specific metrics on the node pool details. So then we have metrics for the node itself, and then we have pod details. Then we also can report the interruption time, and we have dedicated cloud provider metrics. And then of course we have metrics are related to the behavior of Karpenter itself. So it's clearly easy to create a dashboard, not only on the health of Karpenter, but also actually on how our node pool is behaving and how our cluster is behaving. So let's try to utilize those metrics and logs to build a small dashboards to reporting how Karpenter is behaving. Every episode for Is It Observable, there is always a repo, GitHub repo. So here it's the Karpenter repo, of course. So there's all the instructions to build the actual environment. And at the end of the day, to collect the logs or to collect the metrics, in this particular case, I'm using a collector. So the first thing that I'm going to show you is I have two collectors running. One in daemon set, so that's the OpenTelemetry collector CRDs, because I'm using the OpenTelemetry operator. And that will be basically designed to collect the logs from the cluster. So all the pods and including the one from Karpenter. Then we have another one, so a stateful set collector. And this one is going to be also deployed with through the OpenTelemetry operator. And this was going to be focused mainly on traces, metrics, and logs sent through OTLP, because here in this particular case I have the Istio deployed that sends the logs as well. So that's basically how you achieve this, and you can see I have a Prometheus receiver that is scraping the Karpenter metrics, and as a result, here in my particular case, I'm sending it back to Dynatrace. So if you go back to the browser and open Dynatrace, so if you have a Dynatrace tenant, so here I'm opening a notebook, the Karpenter notebook, and I will walk through various things, then we can jump directly to the dashboard. So the first thing I want is to fetch the logs from Karpenter, so filtering on the namespace of Karpenter, and then the message itself provided by Karpenter has a specific structure. So this is where I am, it's a JSON format, so this is why I'm parsing it in a JSON format, and then from there I'm able to collect different properties from that JSON object, so the message, the details of the controller, the time, the logger, and so on, and I do some parser on the actual logs to get even more, a couple of more details about it. But once you have this, it allow me to get the actual details that I need. So the message, what happens at that moment, the controller, the time where this happened, and the level of information that we have. So at the end, with this, it's going to be very easy to basically parse the data that comes from the log perspective. So that's the first piece from a log's perspective. The second piece is the metrics. So if I search for Karpenter here, there's a small component, a widget for metrics. I can press plus if you want to can show you. There's a small metric, a metric widget here. If I enable that, then I can basically walk through the metrics, and in my case I just have to search for Karpenter, and I will have all the relevant metrics that I described. So the cloud provider one, the worker queue, there is specific one for the node claims, the nodes, everything that I've just described with the various families are actually there. So then we can basically go to the dashboard section. So this is the icon for the dashboard, and that will bring me to two of the dashboard I've prepared. So the first one is the cluster overview. So cluster overview has no variables. It shows you just a cluster. And here it's querying the CPU requests in the node pool. And if we just modify this, we can see the actual query. So you can see that I'm querying the node total pod requests, and I'm counting that. I do this, and I splitting them by the node pool. Same thing for the memory, and same thing for the usage. So I have those widgets to show what are the CPU requested, memory requested, and then I also highlight the actual usage. You can also then easily count the number of pods per node pool, so then you can report that as a details. And as a cluster overview, it's always great to see basically how much pods, how much nodes you actually have when scaling up and scaling down. So having that reported. So again, this is going to be a metric. You can see cluster state node count, and you can see the actual nodes. Of course, I can split it by type, but in my case, the actual node was fair enough for me. Then I also, because disruption is a topic, so I wanted to highlight the actual allowed disruptions per node pool. And then in here, I'm adding this node viewer, because Amazon has created a EKS node viewer, so basically listing all the node names, node pool, zone, the type, so spot or on demand. And then I can see how it goes from the CPU allocated, so requests versus allocations, and something for the memory, and I can see some details. So at the end, I give you a view on what happens from a cluster perspective. Then I've added few details on the actual cloud providers. So the duration to do various actions. You can see that there's a create a profile, create tag. So there is a couple of actions going through in this cluster, and I'm reporting that back to this dashboard. So it's mainly if there's an issue and I want to figure out if there's errors, or if I'm spending too much time to spin up in nodes, I have those level of details. I've added the disruptions piece to see the queue, how it goes, the number of nodes that is elected to be drifted. So then you can here it's mainly underutilized. The reason is underutilized most of the time in my particular example. But that I'll always give you. And then at the bottom I'm adding the simulation duration to see how much time it takes for Karpenter to make the simulations before drifting the nodes. And last, you can see I have added this table. It's a first attempt. Again, this could be improved with having more visualizations, but at the end it could be converted as events, because at the end you see we have a process that I described previously, you can follow the actual process, saying here it's registered new claim, it's initialized a new claim, deleted, and so on. So you can see the actual process that I described previously in the video. And last, I'm adding the resource usage of the actual Karpenter replica to see how much CPU core it utilizes, how much memory it utilizes, so you can keep track on that. I added another dashboard, the Karpenter one. In this particular case here, I have created a variable. So here you have basically a dynamic variable similar to what you can find in Prometheus. And I can see here, for example, that I have two node pools, application and default, and then he selected the default now, or the application one. But then I can see the actual CPU requesting that node pool, the usage, the number of node pool, number of pods in number of pods requested in the node pool, allow disruptions, and so on. And then similar to the previous one, but more focused on a specific node pool, I will have the percentage of requested in memory and CPU, the details from the node viewer, and all the various activities about the actual Karpenter. So just with those details, it's very easy to build a dashboard just to visualize how Karpenter behaves over time. And just with this, we can even go further, like I discussed, utilizing logs. having them as events, then you can imagine automation, remediations. So there's plenty of things we can do that with those data. That's it for today's episode related to Karpenter. So Karpenter is a wonderful solution to auto-scale our cluster. Just only the fact that it speed up the startup time of our nodes, that is just amazing. The other thing is, I think the fact that it's simplified the management of all this auto-scaling journey, like creating the management node pool, removing the fact that we have to create those management node pool, the auto-scaling group and so on. I think it's great. So I think the logic of relying on CRD, the node pool one, that define exactly that I need this amount of CPU, this amount of memory, simplifies so much our needs and how on the type of nodes that we need for our cluster. And just on that piece, I think it's great, but I really like the fact that they added the consolidation aspects to basically optimize a bit more the nodes to avoid underutilized nodes. I think that is a great initiative and a great idea at the end. And I think what I was really excited, I thought that Karpenter won't bring much details on how it's working, and in fact I was completely wrong. So the metrics itself is amazing. The logs produced give you all the details that you need, the events, and I didn't touch base on NodeClaim because I think I use mainly the logs, but NodeClaims also get you the details. So I think great initiative. I really clearly recommend everyone to look at it and try it, use it if you're an Azure or AWS customer, because I think it provides so many values and simplifies so much the auto-scaling journey, specifically when you need to add extra nodes in your cluster. If you enjoyed today's content, don't forget to like and subscribe to the channel. So see you soon for another episode. Bye.